Okay. Yeah, so today I thought we'll take a closer look at state replication, right? So we have mentioned state replication before, but we haven't gotten into the nitty-gritty of like how we actually do state replication, what are the ways of doing it, etc. Right? So I mentioned at the beginning itself, the application often would like to replicate their state across various distributed machines for many reasons, but usually it's due to you want to reduce the latency of access of reads at least, and also to provide reliability of the service, right? So if the state is present on more servers, then there won't be there won't be single point of failure in your service. So consequently your service will be more available to your users. So yeah, so replication is sort of raison d'etre of distributed systems. So usually distributed systems exist because we want to replicate the state and control, right? Okay, so each machine, when you're replicating a state across a distributed system, so each machine is set to hold a replica of the state. So we just often say that the machine is just a replica of the state, right? So when you have three machines holding that are replicating the state of an application, so we have three replicas of the application, right? And the goals of replication, as I mentioned, is low latency access to data and resilience, which is data loss prevention, right? And a non-goal of replication, though, is to introduce new behaviors into application, right? So we do not want replication to have any functional significance in terms of application behavior, right? So we want application to run as it was before, but with better latency and throughput, basically better performance, right? But we do not want to introduce behaviors that do not exist previously. So a non-goal of replication is to introduce new behaviors into application. We really do not want that. So if you take that into account, essentially, ideally, we want a distributed system to behave as if it's a single computational unit, right? So we talked about it. So if you have a small service, small application, you can have you can fire up a Linux machine with a SQL database and serve your users. Life is all good. But now your your application has blown up. You've got thousands or millions of users. Now a single machine is no longer sufficient. So you got got hold of a couple more machines. So you have a simple data center for yourself. But the reason you have done it is not because you want to add new features to the application, but rather you want you want your application to scale to hundreds of thousands of users or millions of users, right? But ideally, so that's why ideally, even when you replicate your state across various machines, you want that system to behave as if it's a single computational unit, right? So that's the sort of ideal holy grail scenario. That is, so that's this is a pictorial representation, right? So you have essentially a distributed system consisting of three replicas. So this is ideally you want this to be equivalent to a single machine that serves all the user requests and contains all the user data, all the application data and application control, right? Okay, so when you execute single, when you basically have a single machine which is serving all the user requests, right? So how would that how would the behavior of the machine look like? Like what would the execution history of that machine look like? Right? So let's say you have a single machine here, right? Okay, so you have three users. This is my stick figure drawing. It got a little improved, I think. So three users submitting different requests to R1, R2, R3, right? So let's say you have time. And this is a single machine. Assume it's a single core machine, single control, single memory, and so on, right? So let's say you have a timeline of this way. Okay. So time goes down, right? So how would your how would the timeline look like for the if you were to map the three requests to this timeline, how would they look like?
Should just look like R1, R2, R3.
R3, right? So let's say at some point R1 begins, right? So R1 executes, this is the execution time of R1, right? And R1 ends here. And then sometime after R1 ends, R2 begins. And likewise for R3, right? There's also, and also, by the way, if there is, let's say, for example, you have two users here who's Alice and Bob, and Alice sent request R1. And after R1 came back successful, like R1 is done, then she informs Bob, hey, I've submitted my request. And Bob now submits a request R2. So R2 gets served as well. Right? So there is inherently an ordering between R1 and R2 that's also honored, respected by this, the sequence of execution, right? So essentially we have, sequential execution of requests. Not only is the sequential execution of requests, if I've executed R3 first and then R2 and R1, even then I would have had sequential execution, right? But here we also have another property, which is that sequential execution is consistent with an external notion of time, right? Then notion of time that flows forward. Let's just leave it there. So you have 3 requests submitted by different users, and if ever there is in physical time, if there is an ordering between 3 requests, the ordering is also preserved in the execution history. So execution history looks like R1, R2, and R3. If R2 has happened, was submitted after R1 in real time, then R2 will be executed after R1 in real time, right? So this property is what is known as linearizability, right? So linearizability is where your history of all, your execution history is linear. It doesn't have forking points. It's essentially a linear sequence of operations starting, executing, and finishing. And not only that sequential, but it's consistent with the external notion of the ordering as well, external notion of time. So that's linearizability, right? So,
I have
okay,
a question.
Sure.
With respect to, like, if the system had a scheduler and was looking at R2, and even before R1 executed, completed, R2 gets scheduled in some way due to, so in essence, what I'm saying is, right now you are explaining without a scheduler, and is the presence of a scheduler also incorporated within this notion of linearizability?
Right. So when you have a scheduler, if a scheduler has a choice between 2 processes, let's say, right, would you say those processes are concurrent or sequential? They are concurrent, right? So because they have been submitted concurrently and they are executing concurrently. So in that case, essentially, when you want a linearizable history, you might schedule them in whatever way you like, but the result of executions, right, it should look like as if they have happened in a sequential order. So best example would be database transactions, right? So when you have, let's say R1, R2, R3 are in fact TXN1, TXN2, and TXN3. And let's say this database, whatever you have, the machine is a SQL database, right? So we have SQL databases, assuming that the idealized SQL database, they are ACID compatible, so they provide you serializable transactions. What that means is if you have 3 transactions, TX1, TXN2, TXN3, they might be scheduled in different ways, like TXN1 and TX2 might execute concurrently and so on. But the commits appear as if these transactions have happened sequentially, one after the other. So if your machine is sequentially consistent or is linearizable, then physically you may have concurrency. You may, in reality, in practice, you may have concurrency. But conceptually, the execution should look as if they have multiple requests or multiple transactions have executed sequentially, inconsistent to the total global ordering, inconsistent with the external ordering. Sorry.
Okay.
Does it make sense?
So what you're saying is the linearizability we can talk of linearizability with respect to a scheduler only if the scheduler itself guarantees that it is it operates in the serializable way or something. Like if the scheduler does not guarantee it, then you can't talk about it.
Well, yes. scheduler is part of the system, and the system has to guarantee linearizability, right? So linearizability is not something you can take for granted. So if you have, let's say, if I mentioned 3 requests, R1, R2, and R3. So if you have a single web server process, for instance, right?
Okay. Yeah.
So in that case, essentially you have R1's service, R2 and R3 are put in the queue until R1 gets serviced, and then R2 and R3. Now you have linearizability in that case. But let's say you have multi-threaded web scheduler, web server that concurrently executes R1, R2, and R3. Then the result may not look like as if the 3 have executed sequentially, right? So then it's not, what you have is not a linearizable history.
Okay. Okay. Thank you.
Okay. Okay, so the point of providing linearizability is not that you are going to enforce linearizability all the time, right? So when you have a single database, right, as you mentioned, there is still a chance of concurrently scheduling things and not getting linearizability. That's fine, but at least you have a choice of getting linearizability for the requests that are needed, right? So if you're executing a very sensitive transactions on sensitive data, you might want to have serializable transactions consistent with the external ordering, so linearizable transactions, right? So at least you have a chance of getting that, right? And that's the idealized scenario. So we want the similar choice to be applicable when you replicate the state on a distributed system. So that's the overarching point. Good.
Yes.
Okay. Okay. Okay, so how do we achieve linearizable state replication in a synchronous distributed system? Now, mind you that if you just replicate the state, right? So I think we have discussed this before. If you have 3 replicas, so if let's say if all 3 of them are accepting user requests, then R1 may arrive here, R2 may arrive here, and so on. So which could lead to concurrent execution of R1 and R2, right? So let's say you do not want that. Let's say you want R1, R2, and R3 to be executed sequentially. That is, you want linearizability in terms of state replication, right? So this is caps R1, caps R2, and caps R3. Now, how can you enforce that? Do you know of any techniques or algorithms that let you enforce this sort of linearizable execution on a synchronous distributed system?
So is this kind of, if you're talking of that round robin, a token that moves around, and whoever has the token, and then that is the person that does the execution, then we can say that the final outcome would be a linearizable outcome.
Yeah, true. I mean, that's but when do you pass the token, right? So essentially you have
like if I got R1 as a process and I completed my R1 and then I passed the token.
Yeah, so that's so you're essentially describing this rotating transaction manager, right? So you have R1 initially being, let's say, a transaction manager. It receives all the requests, it applies, it orders them, and after a while the baton passes to R2. So then it's R2's turn to order transactions, and then R3. So that's what you're describing.
Yes.
Okay, good. So that's a first solution. But again, we have discussed the faults with that solution, which is that the processes can crash, and if it's up to R1 to send that token, and if R1 crashes during its while it's processing, then it will never send the token. On the other hand, if you have leases, then you run into the same problems again, right?
Yes.
But we have solved that problem. How did we solve that problem?
We could treat figuring out which request to process first as a consensus problem, and then treat which request to process second as a separate consensus problem.
Excellent, right? That's very good. So essentially, you want consensus among these nodes about the order in which these operations are processed, right? It's a very good solution. It's a good starting point. Let's explore that solution, right? So let's say you have a Paxos implementation P. So as Kirby said, so you can use P to essentially arrive at a consensus on the ordering of processes, ordering of this request, sorry, which among R1, R2, R3 to process first, all followed by and so on. So, okay, so how exactly does it work? Can someone sketch out the details? I have three nodes, R1, R2, and R3, and I have a Paxos instance running on all the nodes that you can use to arrive at a consensus for one value. So let's say you have that and you have requests coming in. How can you use this P to arrive at a consensus for the order in which these requests have to be executed? Here's how you can do it, right? So let's say you have essentially as we have decided, the example that we discussed when discussing Paxos is about agreeing for the value for a given key, right? So given a key, someone might propose a value v1, someone else might propose a value v2. So you have to decide on what value it is, right? So now replace key with n, where n being the index of the operation. That is, all the operations have to execute, all the nodes have to agree on what is the operation corresponding to the index n, right? So let's say until n-1, you have consensus on what are all the operations. What is the first operation, second operation, so on until n-1 operation, you have consensus, let's say, right? Now for the nth operation, essentially you are deciding what is the key for, so let's say you have three, for n, right? So there are three contenders for n, which is R1, R2, and R3. That is the nth operation R1, is the nth operation R2, or is the nth operation R3. So essentially, you're trying to arrive at a consensus for key n among the given set of values, which is R1, R2, and R3. So R1, the caps R1, the replica R1 might propose the request small R1. R2 might propose, sorry, this is R3 and this is R2, right? So R2 might propose a request R2 as the next operation to execute and so on, right? But consensus guarantees that only one among them will be chosen as the nth operation. That means if you have Alice here, Bob here, sorry, Alice here and Bob here, and let's say Cheryl here, right? All of them submitting the operations through different replicas. And until n-1, there is agreement what are all the operations. So now these, R1 says to Alice, hey, wait, let me figure out if I can execute your operation as nth. R2 would say to Bob, let me figure out if I can execute your operation as nth, and so on. Now, since the consensus can only be one value, let's say the value R1 is chosen, then the replica R1, all the replicas would essentially say, hey, look, we have chosen Alice's operation as the nth operation. So Bob and Cheryl have to retry. Their operation has failed, so they have to retry, right? So essentially, you would then choose, for example, nth operation to be R1, n plus 1th operation to be, let's say, R2, and n plus second operation to be R3, right? So here you essentially are using Paxos to get agreement over the values for a given key, where key is nothing but the slot, the index at which you have to execute the particular request, right? Would that work? Are there questions?
Yeah, I think there's a chance that Paxos may not terminate, so some requests may wait forever.
Excellent point, right? So that's good. I mean, so this would at least whenever it terminates, you get a linear sequential execution, right? Okay, but you have a very good point to say. So the downside of this approach is that the Paxos may not terminate, but the overarching point is captured by the cap theorem, right? So you are essentially trying to get strong consistency under a synchronous system. But what does cap theorem say about achieving strong consistency? So cap C is essentially the linearizable consistency, which is strong consistency. So by cap theorem, if you are trying to, if your system has to achieve linearizable strong consistency all the time, then it means that the system is not available during network partitions, right? So if you have the system R1, R2, R3, okay, and so there is a network partition here, and let's say that you're executing, you're trying to get linearizable, strongly consistent state replication, right? So you have network partition. Then you may have the majority partition, running fine because Paxos is okay as long as the majority of nodes work. So let's say you have Alice connecting here, Bob connecting here, and Cheryl connecting here, right? So what happens to poor Cheryl? She can't execute. She's essentially stuck, right? So she can't, she submits a request. Nothing ever gets done from R3. So in essence, the system is not available to some subset of its users, right? So you have lost availability when there is a network partition. So that's one drawback of of a strongly consistent replication. But let's say your network, the partitions are very rare, so you're okay. So cap really doesn't apply, for instance. Okay. Now, what else? In that case, is it fine to just run Paxos to get strongly consistent replication? We have talked about another trade-off that is complementary to cap, right? So the extension or generalization of cap is PASELC, as you have discussed, where we said, okay, either cap, else the trade-off is between latency and consistency, right? So your network is very reliable, partitions are not there, so cap is not applicable, but you still have trade-off between latency and consistency. And so you have chosen to have the highest possible consistency, that is linearizable consistency. It's strong consistency. Strong consistency essentially implies high latency, right? Why high latency? Like, could you give me an example of where there could be really high latency even when there are no network partitions?
Well, if we're using something like Paxos to give us the strong consistency, then that requires just a lot of round trips between nodes for every action.
If you precisely count the number of round trips, right? So you have, let's assume a very idealized execution of Paxos where you have one proposer, no one else is competing, and so on. So you still have 4 round trips of time, round trips of communication needed to establish the value, consensus value, right? So you have prepare, which is 1 round trip, prepare message, you prepare all the rest replicas, then promise from the replicas which agree to the prepare message, followed, and then the proposer then sends an accept message, propose message. And finally, we have accept message, right? And when the majority, when you get the quorum of accepted messages, that is n+1 accept messages, only then you can proceed. But let's say all the accept messages are concurrent, everything's happening so concurrently. So, but even then you have a total of 4 RTTs, which is quite significant if this has to happen over and over again in a distributed system, right? So because network communication is essentially it's next only to disk latency in terms of the amount of time it takes to do that, right? It's a lot slower than network in-memory read, and 4 RTTs is a long time. But also another thing is this is idealized case of Paxos where there are no competing things, right? But when there are multiple proposers that are competing to propose a value for and propose an operation for the nth slot, right? Then only one gets chosen, which means that other one gets delayed until the first one executes, right? So the other one has to retry again. And the weak liveness guarantees of Paxos means that you could essentially wait forever. So essentially, each request might be denied any number of times before it finally gets a slot in the execution sequence, right? So you have basically requests getting repeatedly denied as well. So what this means is it's not, it's very high latency, which means it's practically it's not available. Right? Theoretically, it is available because eventually you'll make progress, assuming everything, there are no partitions and so on. But in practice, it's the high latency is as good as not being available, right? So in that sense, strongly consistent replication, although you get to have this very nice property of being equivalent to single node SQL machine, a single machine, you have this downside of having having to pay such a higher cost in terms of latency, right, or availability. So it's a trade-off. It's okay. For few systems, this trade-off is okay. I mean, especially they have. When you have strongly consistent replication in real systems in certain data centers, right? So they often use highly optimized consensus algorithms. It's a variance of Paxos, or there's another consensus protocol called view replication and so on. So which is more suited for the purpose of replication per se, state replication. So there are such protocols which are highly optimized. So there are systems that use that. But you have to know that when you have such a system, it comes with the trade-off of latency, right? And only when the latency, the cost of latency justifies the benefits you derive from strong consistency, would you choose that? But for many real-world systems that operate at a much larger scale, at the geographical scale and so on, so strongly consistent replication, the latency that arises from such replication is not tolerable, right? It's quite high. It's simply not worth the trade-off. Then what would you have to do then? Let me ask the question in another way, right? So what would have been, so here I've told you one idealized scenario wherein you don't have to change application whatsoever. If you have strongly consistent application, your application as such should work in a distributed system. You don't have to change the application because you essentially have the same sequential behavior. So that would make programmer's job easy, but that would make the user's life hell because they have a lot of latency to deal with. Now let's do another. Let's explore the other side of this trade-off, right? What would be a choice? What would be kind of replication you would have when users are really happy? Like users don't have to wait at all for an operation to succeed, but applications or system administrators have to work really hard to have a working system, to have a well-defined semantics under distribution in on a distributed system. What would such a system look like? Okay, so if you go back to our example, so there is request R1 arriving here, R2 arriving here, R3 arriving here, right? What would be the fastest possible execution path for R1, R2, and R3? Let's forget about how we are replicating the state and so on. What would be the the most idealized scenario in terms for a user who's submitting the request?
So I think ideally all the requests will be executed locally, so they do not really rely on communication to other nodes. Excellent,
right? So as Zhang says, you have Alice submitting request R1 here. An ideal scenario for her would be R1 gets in the caps R1, the replica R1 executes it immediately, produces a result, and just let's say as, hey, Alice, I got your back, I got your request, so you're free to go, right? So Alice is happy and she goes away. Likewise with Bob on R2's end, right? So you get request, you send a request and get response immediately, and R3, right? So essentially local execution. local execution is instead of versus coordinated execution is the trade-off we are considering, right? Coordinated execution. So coordinated execution is strongly consistent replication where replicas coordinate using paxos and so on to decide on the ordering of requests and so on. Local execution is completely uncoordinated. So your replicas are not coordinating to execute requests. So they basically, you have request one executing on one replica to another replica and so on. So you have, things are, from the user's perspective, things are quite fast. But then what's the problem with this uncoordinated local execution?
The states on each node could be very different.
Right. So, so replica states might diverge. Okay. And you no longer have neat, a very, well-reasoned linearizable execution, right? So no linearizability or serializability and so on. So if you look at, if you somehow manage to, get all the states together, even then if you look at how you've arrived at this state from the beginning state, right? So ideally, when even in a linearizable system, in a strongly replicated system, you start from an initial state, let's call it bottom, and you reach a state S after executing R1 to Rn requests. Then essentially, you could derive linearizability guarantees that you can get to S by executing R1 to Rn in some order. For instance, Ri, Rj, R1, Rn minus Rn and Rn minus 1, for instance. So you have some linear ordering, which if you apply on the initial state bottom, you actually get the final state. So that's the that's the guarantee you have in terms of when you have a sequential, linearizable, strongly replicated system, right? But you lose that guarantee once you have once you let your executions, once you let your requests happen concurrently on different replicas, right? So R1, R2, if you, let's say you have a state S under which R1, this request R1, R2, and R3 have executed, then each of it might lead to a state S1, S2, and S3. And now you don't know what the final state is. And even if you somehow manage to reconcile this S1, S2, and S3 into some S4, there is no guarantee that you can go from the bottom state to S4 by a sequence of operations that serializes R1, R2, and R3. So you have lost linearizability in that sense. But is it such a bad thing to lose linearizability? So that's the question that we'll have to ask. Right? Clearly, you can't get linearizability under strong, when your system has to be available under partition tolerance. There are no free lunches. So, and you really do not want to, do not want to have disgruntled users, right? So you do not really want to lose your users. So you want to have fast service and so on. You being application developer would have rather preferred to have strongly consistent replication because it makes your job easy. You don't have to really change your application, get linearizable execution and so on. But alas, you can't have that. So you can't have linearizability. So you have to deal with the possibility of not having linearizability. But is it that bad? Let's take a look, right? So let's say you have, the state that you are maintaining is something very, very simple, like integer counter. You're keeping track of, what do you say? Let's say YouTube views, right? So, which is essentially simply a counter, right? So each of these replicas is essentially a YouTube server. That one is in Asia, one is in Africa, and so on. And there's a very popular video, let's say Gangnam Style or something, which is accumulating views from different continents, right? So you could essentially, there is no need for, each of the increment, let's say you view a video and your friend views it somewhere in Asia. There is no reason, there is no use in essentially sequentializing this request, right? It doesn't matter whether you incremented the view counter first or your friend incremented the view counter first. So in that sense, when you have something as trivial as counting set of views on a video, you really do not need linearizability. So what could you do in that case? Can someone venture an answer? Like what could we do if these are, you have a counter C for a video, it's a Gangnam style video, right? On all the 3 replicas. And you do not want linearizability because it will slow your video service down. So, but you still want to serve users and still want to look at, increment the views and so on. How could you do it? Nick should know the answer. Nick definitely knows the answer.
So since it's a simple counter, so let's say we started off, let's say all of them had the same value to begin with at the beginning of the day. And then the different ones kept incrementing it. The ones in Asia incremented 10 times. The ones in Africa incremented 20 times. And then at the end of the day, at a certain period of time, you can actually try to synchronize all this and see. So what you could do is you would just see by how much did it increment, what's the difference, and then add up all of that.
Right. So assuming that you have, like these are the network will eventually, mend, and you have full connectivity at some point of time. You can send +20 over to here, over here, +10 from here to here, here to here. And so C will eventually be everywhere, C +30, right? So +10 reaches here, +20 reaches here. At some point in the future, it's going to be C +30. And likewise here as well and here as well, right? So you're going to have eventually we're going to have the accurate count of views for a video. So even though in the meantime you cannot really decide whose view has happened first or whose view has happened later. Is it okay in the context of YouTube? Yes, right? Look, who cares if you viewed first or your friend viewed first? You have eventually views being counted. At least the content creators care about the number of views on a video. So you have to count it pretty much somewhat accurately. So you're doing a job, required job. But eventually, right? So the only thing what that can happen, and somewhat not an ideal thing that can happen in the system is essentially a view count at any given point of time need not accurately reflect the exact view count, right? So here, when you, let's say C is initially 300, right? You have just released a video on YouTube. So you've been refreshing and looking at number of views. So at some point you might see 320, right? Because you only gotten this request in on this. I'm sorry, this, yeah. So this count in, but not this one in. So you might see 320. Although at that, if you let the thing settle, if the one that does settles, you actually see 330 because that's the correct view. That's the correct value of the counter, right? So there are these transient faults, transient inconsistencies or anomalies that would eventually mend themselves and going to have this thing, right? Have a eventual convergence. But will it be the case for all the here I've given an example of a simple counter, right? Can I do this for any data type? Counter is simple integer where you're only incrementing. Can I do this trick wherein I buffer the operations, and I eventually release the operations on the network, and all the operations reach everywhere eventually, and you're going to have going to be applied, going to have a consistent state. Can I assume that for all the data structures, data types? You cannot, right? What would be an example of such a data structure, for instance? Some simple data type that does this.
Well, if you had something like a sequence of locations where there were views or something like that, then depending on what order you report those in, or what order a replica hears about those, you'll end up with a different sequence of locations. Maybe that matters, maybe it doesn't.
Yeah, so that's a good. So essentially, you're talking about a list, right? So you have a list of elements. Yeah. If you abstract it away, you essentially have a list of elements x1, x2, x3 on all the nodes. So let me draw it out.
Yeah, and so the problem here is that adding two lists together is not commutable. Whereas
commutable, yeah.
Adding
that's where I'm getting it.
Is.
Right. So you have now appending. Let's say you try to append an operation, some value x4 here, x5 here, and x6 here. So these are all append operations, right? So this is plus append operation. So after appending locally, it's x1, x2, x3, x4, whereas here x1, x2, x3, x6, right? And similarly x5 here. But when append operations reach everywhere, right, you're going to have, let's say, x4 appended after x5 here, and then x6. Here, x5 appending over x6 here, and then x4. And some different order here, x6 and x5. So you will have basically all the elements in the list, but you would not have the ordering. The lists are not the same, right? So not all data types are amenable for this trick. So what data types, what is it required for this trick to be enabled? So as Nick mentioned, so you need to have if you have a data type, all the operations, if you can somehow say that all the operations commute, right? You can ensure that every pair of operations that I do on my data type are commutable, which means that an operation there are op1 and op2. Executing them in this order is same as executing op2 first and then op1 first, which is the case for counter. If you have additions and subtractions, right? So if you have additions and subtractions, essentially because they commute, so addition is commutative, like the subtraction is commutative, and also they both commute with each other. So you have the required for an integer which only has additions and subtractions. You don't need it. This is a straightforward. You can play this trick where you can just replicate and eventually merge. But when you have such as list append, which is not a commutative operation, right? Because the order in which you're appending things matter, they're not commutative. You can't play this trick essentially, right? So this is an observation that was reified formally in terms of this special case of data structures called CRDTs, right? So so these were proposed, I think, in 2011 or so. So the idea is that there are many such data types where either operations are directly commutable, for instance, integers and sets with only additions, etc. Or there are data structures whose operations can be trivially transformed into commutable operations. So that's the observation made by the CRDT folks. It said, okay, so there's enough set of data structures which are rich enough to be run under this non-strongly consistent replication, right? So which means that if you're able to somehow manage to build all your applications with this type of data structures, with CRDTs essentially, then what that means is you need not effectively have you need not need to have a strongly consistent replication. You can run your application. You can serve your requests as and when they come, and you're guaranteed to have a convergent state that preserves the effects of all the effects eventually. Right. So that's the observation event. So CRD, they call it conflict-free replicated data types. Data types. So they have two versions of it. So one is state-based, they call it convergent replicated data types. Depending on the time, I'll go into the details, but otherwise just remember that there is two variants of that. What we have discussed are commutative replicated data types. So CM is commutative, right? So this is where the intuition that if all the operations commute, then you're going to have a convergent state comes in, right? So CVRDTs are based on a little bit different intuition. I'll get there depending on the time, but let's focus on CMRDTs for a while. Okay, so we have seen that a simple counter is naturally a CRDT, CMRDT, therefore a CRDT. therefore a CRDT. What else? Let's take a set, right? If I have only insertions, for instance, is it is it a CRDT? It is, because it doesn't matter like what elements you're inserting. Eventually, when you get all the elements, you have all the elements in the set. But you have additions and removals. Like there is you're deleting. There's a way to delete an element from the set and also remove from add an element to the set. How could you do that? First of all, is that a CRDT? If you have a set which supports both insertions and deletions, it's not a CRDT.
That one, yeah.
Yeah, why? Because when you have an add of an element x followed by remove of x on an empty set, for instance, right? Or let me on an empty set, you have the result as so add followed by remove, right? So essentially you have like empty set again. I don't know. I think I've messed it up a little. So empty set, you add and then remove, so you get an empty set back. But you change the order of operations. You try to remove x, which did not really exist in the set. Then add x, and you get a set of x back. So operations are not commutative. So your set is not straightforwardly CMRDT. But can you make this into can you play some tricks here to make sure that can you still use this data structure under this weakly consistent replication, where you do not have this linearizable, like we are not using Paxos or anything. You still want to play the same trick that you played on counters and so on. Can you somehow get that here in a set with insertions and deletions?
Yeah, it depends on what you want to do with the set. So if it's the kind of set where you're, I don't know, creating event identifiers or something that you'll never see again, then you could use tombstones, where you basically keep a second set of things that have been removed from the set.
Yeah, right. So let's explore that solution first, right? So you have instead of removing from a set, see this is how you do it. Right? Instead of representing a set as a single element, you represent it as a tuple, two sets, one containing the set of added elements, and another containing set of removed elements, right? So the removed elements is as what Nick refers to as tombstones. So essentially these are dead. You're just carrying tombstones for the dead elements. So that might work in that case, right? So let's say you have a set of I don't know. Initially you just have 2, 3, and there are nothing removed. Right? So on one end you might remove 3 but add 4. Right? So since you have removed 3, you add 3 here, right? So on the other end, let's say this is on one replica. On the other end, you might remove 2 but added 5. So you have 3 and 5. So you remove 2. So here, right? So let me write it down here. Add 5, remove 2, and here add 4, remove 3, right? So now when these operations are eventually applied here, what would happen? What would you get? It's a tuple of 2 sets. What would be in the first set?
Four and 5.
4 and 5, right? So because when you apply remove 2 here, 2 goes into, so okay, 2 goes here. When you apply add 5, add comes here, 5 comes here, right? And you have 2 and 3 anyway.
Yes.
Likewise, make sense?
Yes.
Okay. Okay. Likewise, if you do the same thing, if you take these things here and apply them here, I'm sorry. Yeah, what would you get?
Same 4, 5, and 2, 3.
Right. So essentially, this means that you have a set which only contains the elements 5 and 4 and 5. In case, for instance, let's say if, for the sake of this example, initially I had 1 here as well, and here I've removed 1. Right. Do I need? Actually, I don't. Okay. This is. I think let's leave the example there, right? So you have set of elements and the set of tombstones. So essentially, when you have an insertion attempt to insertion later, right? So you can see that if you have element that has already been deleted, you might choose not to re-add the element again, for instance. So that's what did I say it correctly, Nick? So essentially, you have only insert only once property. If you have such a property, you can have essentially a set of added elements and a set of deleted elements. So once deleted, an element is deleted forever, so you will not have it ever again. So you will have convergence as a result.
Mm-hmm.
So
and you could also just leave the elements in the inserted set and just sort of understand that if they're also in the remove set, you should read them as not in the set.
Yeah, right.
And
so
then you can see that really all this is just 2 add-on
set union.
Sets.
Yeah. So okay, that's correct. I think I was corrupted by MRDTs, this is how we do it in MRDTs, where we do the state merging. Okay, so yeah, so when you so let me then take this somewhere else, right? Oh, sorry. Okay. Okay, let me decide here. So there's no 1 here. So let's say you have, when you add 4 and remove 3, instead of actually changing the set here, you could just add 4, do nothing to 3, but just add 3 here. Right? Likewise, when you add 5 and remove 2 here, you don't actually remove 2 from the inserted elements. You just have 2, 3, and 5. So once you merge, get these things. So add 5 gets added. So do this. If you don't have to remove the element from the first set. You will then have 2, 4, 3, 5, and when this set will be simply the union, which would be 2 and 3. Right? Same would happen here. So if you're not removing elements from the first from the set, you have 2, 3, 5. Then you have add 4 and remove 3. Remove 3 will show up just as an insertion into this set, and add 4 will simply be 2, 3, 4, and 5. And now looking at this state, okay. So looking at this state, you can, what's the set of elements that is present? So it's adds minus deletes, right? So essentially,
yeah, just 4 and 5.
3, 5 minus 2, 3, which is just 4 and 5. Same here as well, 4 and 5. So you have essentially, instead of one set which grows and also decreases, when you have additions and insertions and deletions, if you do it naively, you have one set which grows and also shrinks, right? Instead of having that, you have you keep track of 2 sets which monotonically increase. So, and you compute the actual set as a difference of these two monotonic sets, right? So that's, this way you can essentially have, you've transformed a data structure, a set which is not really commutative, into another data structure, which still represents set, but nonetheless has commutative operations. There are, of course, caveats, like for instance here, once deleted, an element is deleted forever. You cannot say add, once you try to, let's say someone comes and says, oh, let me re-add 2 now, right? So you look at 2 here, 2 is already present, so you don't do anything. So do you still have 2, 3, 2, 4, 3, 5, right? So 2 is still here. So if you compute the elements, even let's say this is add 2, right? So you would still get 4, 5 as the result, right? So an element deleted once is deleted forever. So if you are okay with that property, essentially you can have a version of set which is commutative. So there are this set of tricks that you can play with various data structures to get them to lose a few properties, but nonetheless make them robust enough to be used under weakly consistent replication, a replication where you do not have Paxos consensus, right? So there is a whole series of, there's a cottage industry and producing this CRDT papers. You have this variance of CRDTs for various things, for instance, JSONs, or document editing data structures, or queues, not queues actually, lists and whatnot, right? So that's the engineering trade-off you make, right? So instead, if you don't want your users to suffer, so you want the operations to be really fast, but at the same time, you do not want to completely mess up your state. So the way you can do it is essentially by coming up with this sort of a re-engineering of your data in a way that actually preserves, in a way that actually converges eventually and preserves the user intent, right? So that's essentially what CRDTs are about. So I have my own take on these replicate data types. I call them mergeable replicate data types. So they are technically a little different from CRDTs, but the intuition is nonetheless the same. So you have, if you do not get linearizable history, but you're still okay. You still have sensible semantics for your data structures. In that the ways of doing those things is a little different. So CRDTs do it in some way, and I do it in a little different way. So that's it. Okay. What else I want to talk about? Okay. So let's say you have your you have engineered your entire state into something like this, where you have commutative or convergent replicated data structures or mergeable replicated data structures. So what that means is eventually you're going to have all the states converging into a single convergent state that somehow represents the intent of all the operations submitted so far, right? So let's say you've managed to do that. Very good for you. You now have an excellent application. But is that enough, or is there anything that can still go wrong?
Well, it depends on what the requests do with the values they see, I guess you could say.
Oh, you are. I see. No, that's true. So you are getting to the point wherein there are invariants on the data, and the invariants get violated and whatnot, right? Sure, that can happen. Okay, maybe that would lead me to the point that I want to make. Let's consider that point, right? So let's say
I think I had a nice example with the YouTube counter. Say YouTube was running a promotion or something where the millionth viewer gets $1 million.
Okay.
So you can get that by counting the views, but then you have this issue of, okay, if you log a view and it says it's the millionth one, do you give them the $1 million, or what are you going to do?
Yeah. So you don't know, right? It's because you have a millionth view can happen on 3 different places or 2 different places, and who's going to get the award now? If you're going to award to all of them, then you're going to lose multiple $1 million. And in fact, that can be gained to have so many. By cleverly blocking your network, you can keep on minting millions of dollars from YouTube in that case. Yeah, so those things can happen, right? Okay, so that's example of an anomaly. I'll tell you one other example of an anomaly. Maybe you could tell me like what is common among these things, right? Let's say, what would be another simple example? Let's say you're a banking application, which is the canonical one. You have, should I? Okay, so here's the thing, right? So I have a banking application and I have certain amount of balance in that application. And whenever the balance falls below a certain minimum balance, let's say below $500 or so, I'm going to impose an overdraft penalty or something like that. Like I'm going to impose a penalty on the user, right? There is, let's say you start with the balance of 600 or so, and there are two separate replicas which have concurrently did okay, here is okay, no, not the concurrent withdrawals, but let's say you have you started with the balance of, let's say, 500, then you added 200 on one replica and withdrawn $100 at a different replica. So it's plus 200 and minus 100. So on the minus 100 side, on the plus 200 side, nothing happens. So 500 goes to 700, you're fine. But on the minus 100 side, you subtract 100, you go to 400, and immediately the balance, the minimum balance check kicks in, and the user is going to be imposed a penalty, right? And once the states merge, you eventually are back to being in a good standing. So you have 500 minus 100 plus 200, which is essentially a positive deposit of $100. So you ideally shouldn't have been imposed a penalty, but maybe due to network transient faults, these requests did not happen at a single replica. They happened at a different replica. So you are imposing a penalty on the user, where on the bank account user, when he really didn't do anything incorrect, right? So this is another example. Well, let's take a look at these two examples and see like what is it like, what is the characteristic of the application that has led to these anomalies. So here's a thing, right? So observation is among these applications, you have the state. The state is convergent. Eventually, all the states. In the case of YouTube counter, the counter is going to converge. You're going to have 1 million or 1,000,003 views, 1,000,004 views eventually. Likewise, in the case of bank account, the balance is going to converge. It's going to reflect the accurate balance, maybe in a few seconds of time or so. But there's something that has happened in the intermediary time that has, that has essentially disturbed your application semantics, or broken few things, right? Now, what has happened intermittently, and what is the characteristic of the computation that has happened in the intermediate time?
I guess you could think of it as a side effect has occurred. Where, like the end output value is the same in either case, but depending on the order in which it was put together, a side effect has occurred, and the question then is, can you undo that side effect?
So yeah, so you to slightly paraphrase your observation, a side effect has occurred, which once you reconcile the states has to be revoked. There is a need to revoke that side effect once the state has merged. In other words, your computation that you have done is non-monotonic, right? So it makes a certain decision, then instead of piling up on the decision, but if as and when it gets new data, there is a chance that you're going to revoke that decision and go to a new decision. So this is what is called a non-monotonic computation, right? So where you do not simply keep on, a decision once made is not made forever, but it's actually could be revoked, right? So that's non-monotonic computation. Right. So the observation here being that even when you have fully convergent state, if your computation, the data is fine, but if your computation is non-monotonic, if you're going to change your decisions based on the new data arriving, right? So what that means is you still can run into issues, right? You still can have faults. So so CRDTs is only CRDTs or whatever sort of these replicate data types. Oh, sorry, DTs, right? Is only one part of the solution. You need something else, and that is stated by a theorem called COM theorem, right? So Nick, are you aware of this? Okay. So COM theorem is essentially consistency as logical monotonicity. Right? So so what it says is essentially, okay, you need to have your data which is going to be eventually convergent. That's great, but you also need your computation to be logically monotonous. It need not be physically monotonous in the sense that you're not going to, it need not look as if you're computing a set which is going to increase all the time, or a number you're going to increase all the time. But in the logical, in the semantic sense, your computation has to be monotonic in the sense that a decision once made cannot be revoked. If you can somehow manage to write your computation in terms of logical monotonic, express it as a logically monotonic computation, and you have a data which is commutative, convergent, right? So put together, you have an application that works correctly. Application working correctly under weak consistency. So this is the holy grail. So you want your application to work correctly without any coordination, without paxos or anything, because you don't want your users to suffer. So the engineering techniques, or the thing that way you arrive at that, is essentially by changing your data so that your data is conflict free. You refactor it in terms of CRDTs or MRDTs or whatever, and your computation has to be logically monotonous. You make sure that decision, the way you compute things and so on is only grows. That your decision once made cannot be revoked, etc. If ever there is a need to make such a computation where you have to make a decision that has to be revoked, there is no choice but to introduce this bottleneck in your path where you synchronize and do that computation. Right? For instance, the simplest example is withdraw. If you really do not ever want balance to go below minimum balance, right? Then you might want to have withdraw as a strongly consistent operation, right? Wherein all nodes synchronize to do that operation, and then you move on and do other operations without synchronization. So in that sense, so CRDTs and the COM is a theorem, right? So it's actually a formally proven theorem. So COM theorem essentially are both positive results and negative results. Positive results because they give you a way to rewrite your computation and in a way you don't need coordination. Your latency can be very low. But they are also negative results in the sense that if you cannot express your computation in a logically monotonic form, then there is no way you can execute it without synchronization. So that's why COM theorem is sort of powerful, right? So essentially, it's both it's sound and complete. So you have to, if you cannot express your computation as in a logically monotonic form, you cannot do it without synchronization. You have to introduce synchronization to do that part of computation, right? But at least the good news is that now you have a way of teasing out those parts of your computation that are not logically monotonic and synchronize for only those parts, and do not synchronize for the other parts which are trivially logically monotonic, right? So you can do that sort of refactoring. So that's where the selective use of selective strengthening of consistency and the selective use of paxos or something comes in. And that's a lot more, that sort of lets you have the best of both worlds, right? You can have consistency or strongly consistent replication for sensitive piece of data and sensitive forms of computation. And the weakly consistent replication, or like no coordination replication for the rest of your operations. And that's usually how the applications that are designed on top of distributed systems are often that's at least the theoretically correct way of designing applications on top of distributed systems. Of course, in practice, people make lots of different trade-offs as well.